Assalamualaikum warahmatullahi wabarakatuh. Perkenalkan, nama saya Aga Ilham. Saya dari jurusan Teknik Mesin Universitas Negeri Padang. Nah, di video kali ini saya akan menjelaskan tentang pengujian logam yang mencakup dari definisi pengujian logam, kemudian metode yang digunakan pada saat pengujian logam tersebut, dan tujuan serta hasil yang didapat dari pengujian tersebut. Nah, kita langsung saja ke materinya.
The Brinell hardness test. Using the Brinell method, the hardness of a turbocharger housing is to be measured. First of all, the tester has to make himself familiar with the testing machine. A monitor and the control panel are positioned in the upper part of the machine. These are used to select and program different testing methods. Below the control panel, a microscope lens with a digital camera and an indenter are installed. These two elements are connected to each other and rotate towards the test piece as required. It is also possible to select and exchange the indenter, so different methods of hardness testing can be conducted on the same testing machine. The support table can be adjusted in height, so the test piece can be positioned at the correct distance to the microscope lens and the indenter. After becoming familiar with the machine, let's start the experiment. The principle of the Brinell hardness test is to press a hard spherical indenter with an exactly defined force onto the test piece, then evaluate the surface area of the indentation. The tester selects a suitable spherical indenter and inserts it into the holding device of the testing machine. Next, he puts the turbocharger housing onto the support table, rotates the microscope lens into vertical position and adjusts the correct height of the test piece. After bringing the test piece surface into focus, he selects the exact spot where the hardness test is to be made. By pushing the start button, the hardness test procedure begins. The testing machine rotates the lens back to its resting position and places the spherical indenter carefully on the test piece surface. Gradually and shock-free, the test force rises to its specified value. After maintaining the test force for a certain time, the indenter automatically lifts off again and the microscope lens pans back to its former position. The indentation can now clearly be seen on the monitor. With the control knob, the tester places 4 measuring lines on the edges of the indentation to measure its diameter. That's it! The testing machine can now calculate the Brinell hardness. The hardness value is defined as test force F in the old unit kilopond divided by the area of the indentation A in square millimeters. The result is displayed on the bottom left-hand corner of the screen and amounts to 250. The Charpy Impact Test. The standardized Charpy Impact Test has been designed to measure the toughness of materials under impact loading and multi-axial stress state. A pendulum impact testing machine is used to do so. The pendulum on the machine has a heavy weight at the end. This is lifted into the starting position in step 1. Then the tester checks whether the testing machine has been adjusted accurately. In order to do this, he turns the drag indicator downwards and releases the pendulum without a test specimen. The drag indicator stops at position 0. This proves that the pendulum has the correct starting position and that the friction is correctly compensated. The machine is ready for the tests. First test, strain-aged plain carbon steel S235. This is our test specimen. It has been machined to standardized size and shape with the characteristic V-shaped notch. The tester places the specimen on a support in the lower part of the machine and adjusts its position with a centering device. Next, he turns the drag indicator downwards again and checks that everything is prepared correctly. Perfect, the test can begin. The pendulum is released, it swings downwards and hits the specimen with its rounded hammer peen. The specimen absorbs part of the pendulum's energy, so the pendulum doesn't reach the full height on the other side. The amount of energy that has been absorbed by the specimen can now be read off at the position of the drag indicator. It only amounts to 13 joules in this test. Here is the main principle of the measurement. In its starting position, the pendulum only has potential energy. It is given by mass of the hammer m times gravitational acceleration g times starting height capital H. After the pendulum has been released, the hammer moves downwards, hits the specimen and then only swings to height small h. Exactly at the first reversal point, the pendulum again only has potential energy, which is m times g times small h. The energy that has been absorbed by the specimen is called notch impact energy, kV. It corresponds to the difference between the two potential energies. The first specimen only shows very little plastic deformation. A mostly flat, slightly glittering fracture surface has been formed. This is another important indication that this kind of steel is only able to absorb small amounts of notch impact energy. It shows mainly brittle behaviour due to the strain aging effect. Second test. The second specimen has been made from normalised steel S235. It is also placed on the support and centred. The tester turns the drag indicator to its starting position, rechecks all safety measures and releases the pendulum. This time the impact sounds much deeper and richer. An impressive energy of 182 joules has been absorbed by the specimen. Here the specimen did not break into two pieces. Instead it was pushed through the counter bearings under heavy plastic deformation. In comparison with the strain-aged steel, the normalised steel absorbs much more notch impact energy and behaves in a very tough manner. The Charpy impact test is not only carried out at room temperature. Materials with body-centered cubic crystal structure, such as plain carbon steels, show a characteristic S-shaped curve of the impact energy versus temperature. In the so-called upper shelf region, the material absorbs a lot of energy and behaves in a tough manner. At low temperatures, in the lower shelf region, only a small amount of impact energy is absorbed and brittle fractures occur. Metallic materials with a face-centered cubic crystal structure, on the other hand, do not experience a ductile to brittle transition. These materials retain their ductile behavior towards low temperatures and are therefore well suited for low temperature applications. The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 mm and an original gauge length of 100 mm. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 mm. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Luders effect. After a certain strain, known as the Luder strain, the force increases again. The material opposes an increasing force against the imposed elongation. Its strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength RM. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test, a material without yield point phenomenon is to be tested. In this case, it is a precipitation-strengthened aluminium alloy. The test piece has exactly the same shape and dimensions as the specimen in the first test. It is cylindrical, with an original diameter of 10 mm and an original gauge length of 100 mm. After fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start. The initial linear curve in the force elongation diagram again shows the elastic behavior of the material. But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change. There is a smooth and gradual transition from linear elastic behavior to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there. As a common substitute for the yield strength, the 0.2% proof strength is used. It is the stress that causes 0.2% of plastic deformation in the material. And this is the way to calculate it. First of all, the elongation that corresponds to 0.2% of strain has to be computed. For an initial gauge length of 100 mm, the result is 0.2 mm. In the force elongation diagram, a straight line parallel to the elastic line is drawn through the offset point of 0.2 mm of elongation. The force at the intersection point of the offset line with the force elongation diagram is designated as Fp 0.2. This is the force that causes a plastic strain of 0.2%. The 0.2% proof strength, Rp 0.2, is equal to Fp 0.2 divided by the original cross-sectional area S0. Tensile strength, percentage elongation after fracture, and percentage reduction of area are calculated in the same way as in the first test.
Metallography Part 1 gives an answer. In this video, we would like to introduce the macroscopic techniques of metallography. Macroscopic means to investigate a workpiece over a comparatively large area. Doing this, only little or no magnification is required. Often the naked eye is sufficient to examine the material. As a first sample, we are going to investigate an ingot made from an aluminium alloy. To have a look at the inside, the material tester has to start with a raw cut through the ingot. She picks up the ingot and carries it from the laboratory to the mechanical workshop. The bandsaw machine has already been prepared. The ingot is positioned on the saw table so that the red laser marking line indicates the intended cutting plane. Clamping jaws fix the ingot securely. Then the bandsaw gently sets onto the block and cuts it slowly under intensive liquid cooling. It is important to keep the material as cool as possible to avoid changes in the material structure. That's it, the ingot has been sectioned. Back into the lab, not much is to be seen on the cross-section apart from the typical saw marks. In the next step, the material tester removes the saw marks by careful wet grinding with silicon carbide paper. On the one hand, this serves to produce a flat surface. On the other hand, the plastic deformations are removed that were generated by sawing. After the first grinding operation with coarse-grained paper, the material tester rotates the sample by 90 degrees and grinds it once more, this time with medium-grained silicon carbide paper. Here again she uses sufficient flushing with water. This keeps the sample cool and prevents the abrasive paper from being loaded with material particles. Now a flat, medium ground surface has been created, but apart from the grinding marks, nothing special can be seen. Our sample reveals its structure only by the final etching process. After washing and drying the sample, the material tester dips the ground surface into a suitable etchant. In this case, the etchant consists of a mixture of different acids. Special care should be taken here. The material tester protects herself with a lab coat, special gloves and safety glasses. After half a minute of contact time with the etchant, she washes the sample thoroughly with water and gently wipes off the grey coat of particles using cotton wool. In the last step, she rinses the clean surface with alcohol and lets it dry under a hairdryer. Now the specimen preparation is finished. Beautiful bright and dark shimmering crystals can be seen. In technical terminology, these crystals are called grains. In the central and lower region of the sample, the grains are comparatively small. They are hardly visible with the naked eye. But in the upper part, large individual grains may clearly be distinguished. But why are the grains only visible after etching? The reason for this is that the etchant structures the material grains on the surface according to their crystal orientation. Experts call it grain contrast etching. At lateral illumination, the individually structured grains reflect the light in different directions, and the grains become visible. As a second sample, the material tester examines a piston from a petrol engine of a passenger car. The procedure is the same as before. Careful sectioning under liquid cooling is followed by wet grinding with coarse-grained paper, then wet grinding with medium-grained paper, and finally the decisive step, the etching. After washing, cleaning and drying, fantastic crystals are visible again. It should not be concealed that these crystals, these grains, are not perfect and uniformly structured crystals, but so-called primary grains. Within the primary grains, many other very small crystals and also crystal defects may be found, but these can only be seen with appropriate microscopes. Virtually all materials of our world can be examined metallographically. To show part of that variety, we will look at some additional test pieces made from different steels. All of these samples have been sectioned first. Some of them are so small that they have been mounted in resin for easier handling. And all of the samples have been wet ground with medium-grade abrasive paper. This was done towards the end of the preparation, as shown here in the case of the tooth of a gear wheel. After grinding, not much is visible except from the typical grinding marks. As before, the internal structure will only be revealed by etching. But now the material tester uses a different etchant. This time it is nitric acid diluted in ethanol. She holds the mounted sample with pliers and immerses it into the etchant. After a few seconds, she takes the sample out again, washes it thoroughly with water, then with alcohol, and finally dries it with a hairdryer. Now the preparation of the flame-hardened tooth of a gear wheel is finished. In this case, the individual grains cannot be seen, they are far too small. But what may be seen very well is the hardened zone, which appears light, and the central soft and tough region, which appears dark. Next in line is the section of an induction-hardened cylindrical shaft. The comparatively soft core is much more affected by the etchant than the hardened surface layer. Clearly, the induction-hardened surface layer can be distinguished by its light color from the darker core. This section of a splined shaft is induction-hardened as well. As a result of the etching process, the outline of the hardened surface layer may easily be recognized. The dark area represents the core that has not been hardened. This is a tooth from a case-hardened gear wheel. The surface region of the gear wheel has first been carburized at high temperature and then quenched. The etched sample shows the smooth transition from the carburized and hardened surface region to the softer interior. Weld joints can also be examined metallographically. In our case, the etching process takes a little more time and the analysis is more difficult. But by and by, the structure inside the steel plates, the position of the weld passes, and the heat-affected zones may be identified with a skilled eye. Even in everyday life, one meets metallography. At this hot-dip galvanized lamppost, the rainwater has acted as an etchant over the years. The large flat zinc crystals have been structured on the surface and can be recognized as so-called spangle. Even inside of a tin plate steel can, crystals are visible. The fruit acid of pineapples has etched the flat crystals of the tin coating. A natural and unintentional grain contrast etching process has taken place. On the outside, the tin coating is still unchanged and shines like new.